All right, we're going to look at an example problem on this idea of simultaneity and how events in reference frames, how we describe them, are they happening at the same time, are they simultaneous, and if not, how would we describe them depending on where we are relative to that reference frame, or within that reference frame, excuse me. So we're going to look at this example. You're standing at position 9 kilometers and your assistant is at position 3 kilometers. Now there's 2 lightning strikes. Strike A is going to happen at 0 kilometers, and strike B happens at 12 kilometers. You observe lightning bolt B at time equal to 10 microseconds. You observe lightning bolt A at time equal 50 microseconds. So what would your assistant say about the simultaneity of these 2 events? Are they simultaneous? If they are, great. If they're not, how much time is in between them? So we're going to use the information that we have about you to determine when these lightning bolts actually struck. Okay. So let's start with lightning bolt A. We know that the change in time for anything is relative to how fast the object is moving, and in this case that object is light, is the distance over the speed of that situation, so the speed of light. So how long it takes for you to see a flash of light is how far out you are away from that flash and the speed of light. And so for lightning bolt A, your change in time is equal to the distance, which is our 9 times 10 to the 3rd meters, divided by the speed that light travels, which is 3 times 10 to the 8th meters per second. So how long it takes for lightning bolt A to reach you is 30 times 10 to the minus 6 seconds, 30 microseconds. Okay, and I'm just going to use the kind of standard units that we use for these blocks of time. So it takes 30 microseconds to get to you. Now that's the change in time. So that's T final minus T initial equals 30 times 10 to the minus 6 seconds. Well, we know it gets to you at 50. So T initial is going to be 50 minus 30, or 20 times 10 to the minus 6 seconds. So lightning bolt A happens at 20 microseconds. Oops, that says microcoulombs. At T equals 20 microseconds. That's when it happens. Okay? Well, what about lightning bolt B? Does it also happen at T equals 20 microseconds? Well, let's check it out. We know the change in time for lightning bolt B is going to be the distance lightning bolt B travels divided by the speed of light. Well, lightning bolt B travels 3 times 10 to the 3rd meters, 3 kilometers, over our 3 times 10 to the 8th meters per second. It takes 10 microseconds, or 10 times 10 to the minus 6 seconds, to get to you. Well, T final minus T initial, that's our change in temperature, our change in time. We see it at 10 microseconds. If we see it at 10 microseconds and it took 10 microseconds to get to us, well then the time for B was at T equals 0. So B was at T equals 0. A had to happen at T equals 20 microseconds. They did not happen simultaneously. B happened 20 microseconds before A. Now, what does your assistant say about that? You and your assistant are in the same reference frame, and therefore your assistant would agree with you. Also have to say that these 2 bolts of lightning did not hit at the same time. You are both within the same reference frame. You're at rest relative to that reference frame. Okay? But is that what your assistant observes? Let's just look at that to get the appreciation that they might not observe them simultaneously, just like you did not observe them simultaneously, or they might. So let's look at what the assistant observes. The change in time for the assistant is, of course, equal to the distance divided by the speed of sound. Light, the speed of light. The assistant is 3 kilometers, so 3 times 10 to the third over the speed of light, which is 3 times 10 to the eighth. So the change in time for the assistant is 10 microseconds. So the assistant hears light A 10 microseconds after lightning A strikes. We know lightning A, so that's T final minus T initial is equal to 10 microseconds. The difference, T initial we know is 20, so T final is equal to 30 microseconds. The assistant hears, or sees, lightning A at 30 microseconds. What about B? Well, we can find the same idea, use the same principle. Delta T is equal to the distance over the speed of light. The distance that the assistant is from lightning strike B is 9 kilometers. So 9 times 10 to the third meters. And of course, light travels at 3 times 10 to the eighth meters per second. So the change in time that it takes, the amount of time it takes for the light to hit the assistant is 30 microseconds. That's the change in time. Delta T, T1 minus, T final minus T initial, it's delta T, T final minus T initial is equal to 30 microseconds. We know that based on the information, the timing information we had from me, we know from you that the initial time for lightning strike B was at 0. So T final is equal to 30 microseconds. So the assistant hears A and B at the exact same time. They see A and B at the same time. But because they are at rest in this reference frame, they know that they're not happening simultaneously, even though they see them simultaneously. So that just gives you an idea that that observation is now different than what's actually happening in terms of the timing of these two lightning strikes. So simultaneous doesn't always mean you're experiencing them at the same time. It means they're happening at the same time. And in this case, they are happening at the same time because they're within the same reference frame, the assistant and you. But as we learned when we introduced the idea of simultaneity, if one of the observers is moving, then something can be simultaneous in one reference frame and not in another. So just to kind of help you wrap your head around all that simultaneity stuff and its relationship to the theory of special relativity. Good job.